A helical antenna is a specialized type of radio frequency antenna where the conducting wire is wound into the shape of a coil or helix, typically mounted over a flat reflecting ground plane. What makes the helical antenna unique is its versatility. Its electrical behavior changes drastically depending on the physical size of the coil relative to the wavelength of the signal it is handling. It operates in two primary, completely distinct modes. Normal mode, broadside. In this mode, the dimensions of the helix, the diameter and the pitch between turns are very small compared to the wavelength of the operating frequency. Radiation pattern. The antenna radiates perpendicular to the axis of the coil, similar to a standard dipole or monopole. Polarization linear. Practical use. This design is used to drastically reduce the physical size of an antenna while maintaining electrical resonance. It is the core concept behind the rubber ducky antennas on handheld transceivers. In HF applications, winding a wire spirally around a fiberglass mast is a highly effective way to build a shortened vertical whip for lower frequency bands like 80 meter or 160 meter. It allows you to fit a resonant antenna into a much smaller physical footprint, though the trade-off is a significantly narrower bandwidth and lower radiation efficiency compared to a full-sized wire element. Axial mode and fire. In this mode, the circumference of the coil is roughly equal to one full wavelength and the spacing between each turn is roughly a quarter of a wavelength. Radiation pattern. The antenna acts directionally, firing a beam of radio frequency energy straight down the axis of the coil like a flashlight. Polarization. Circular. The wave rotates as it travels, either right-handed or left-handed, matching the direction the wire is wound. Practical use. This mode is exceptional for space and satellite communications. When communicating with tumbling low Earth orbit satellites or penetrating the ionosphere, signals suffer from Faraday rotation, meaning the polarization angle of the signal twists unpredictably. If you use a linearly polarized antenna like a standard Yagi, you will experience severe fading when the signals cross-polarize. A circularly polarized axial helical antenna completely mitigates this fading, making it a powerhouse for reliable satellite links. Designing a helical antenna for the 160 meter band, the top band from 1.8 to 2 megahertz, that is not in my region but almost globally, means you are building a normal mode helical antenna. A full-sized quarter wave vertical for 160 meter requires a staggering 40 meters, 130 feet of physical height. Winding the wire as a continuous coil around a non-conductive mast essentially creates a continuously loaded vertical whip. This compresses the necessary electrical length into a physically manageable size, making it a highly practical homebrew project for constrained spaces. Key design considerations for 160 meter. The former, that is a mast, you will need a sturdy RF transparent material. Heavy duty PVC pipe, 2-inch or 3-inch diameter, or a fiberglass mast are the best choices. The larger the diameter of the former, the wider the operational bandwidth will be. The wire. Enamel coated copper wire, that is the magnet wire, or standard insulated house wire works well. For a 160 meter transmitting antenna handling 100 watts, 14 AWG nearest to 2.5 square millimeter wire or 12 AWG wire is recommended, to minimize resistive losses in the coil. The ground system, critical, because this is a highly shortened antenna. The radiation resistance at the feed point will be exceedingly low, often under 5 ohms. If your ground resistance is high, your transmit power will heat the dirt instead of radiating into the air. An extensive system of radials laid on or under the ground is absolutely mandatory for this antenna to be effective. Impedance matching. The feed point will not be 50 ohms. You will likely need an L network matching unit at the base of the antenna to step up the low impedance to match your coaxial cable and transceiver. Calculating dimensions. Designing a normal mode helix requires finding a balance between the physical length you can support and the amount of wire required to achieve electrical resonance. A standard empirical rule of thumb for continuously loaded quarter wave equivalent is that the length of the wire required will be approximately 50% of the physical wavelength. Here is the textbook-based breakdown of the design calculations and steps for building a 160 meter normal mode helical antenna. The core formulas. To design the continuously loaded vertical, you need to calculate the total length of wire required to achieve electrical resonance and then figure out how to distribute that wire over your chosen physical mast. Wavelength lambda is equal to 300 by f, where f is the target frequency in megahertz. Approximate wire length. A standard empirical rule is that the required wire length is roughly half the wavelength, that is 0.5 lambda. Circumference per turn, C, is equal to pi into d, where d is the outer diameter of your mast. Total number of turns, n is equal to total wire length divided by C, that is circumference per turn. Turn spacing equal to physical height of the mast divided by n, the number of turns. A practical example build. Let us assume you are targeting 1.85 MHz, again not the VU band. You are using a standard 50 mm approximately 2-inch PVC pipe as your former, and you want the physical antenna to be 5 meters tall. Target frequency 1.85 MHz, wavelength 300 by 1.85, approximately 162.16 meters. Required wire length 162.16 into 0.5, about 81.08 meters of wire. Circumference of 50 mm PVC, pi into 0.05, about 0.157 meters per turn. Total turns needed 81.08 divided by 0.157, around 516 turns. Spacing between turns 5000 mm, that is the length of the pipe, divided by 516, around 9.7 mm spacing between each wrap. Construction and tuning nodes. Wire selection. When pushing 100 watt using 14 AWG or 12 AWG enameled copper wire, that is magnet wire, is highly recommended. The lower the gauge, the better you will minimize resistive losses in the tightly wound coil. The ground system. This is the make or break component. A drastically shortened 160 meter vertical will have an extremely low feed point radiation resistance, often single digits. Without an extensive network of ground radials laid out at the base, your RF energy will dissipate as heat into the soil rather than radiating. Impedance matching. The feed point impedance will not be a flat 50 ohms. You will need an L network matching unit installed directly at the base of the antenna to step up the impedance to match your transceiver and coax. Final alignment. The 0.5 lambda rule for wire length is just a theoretical starting point. Stray capacitance from the PVC former, the wire insulation, and nearby objects will shift the resonance. It is best to wind about 5 to 10% more wire than the math dictates. Use an antenna analyzer or VNA at the base, measure the actual resonant frequency, and slowly prune the wire or adjust the compression of the top turns to dial it precisely into 1.85 MHz. Moving to the VU160 band, which is from 1.8 to 1.825 MHz only. The narrow 25 kHz window makes perfect sense for your regional allocations, and it actually works entirely to your advantage here. Normal mode helical antennas have inherently narrow bandwidths, often right around 20 to 30 kHz on the 160 meter band. This means once you tune it to the center of your band, you likely won't need an antenna tuner to cover the rest of that specific segment. To optimize for this, we should target the exact center of your allocation, 1.8125 MHz. Here is how the theoretical math shifts for that frequency, assuming the same 5 meter physical length and 50 mm former from the previous example. Wavelength 300 by 1.8125 is equal to 165.51 meters. Target wire length 0.5 lambda, 82.76 meters of wire. Total turns needed 82.76 divided by 0.157, around 527 turns. Spacing between turns 5000 by 527, around 9.48 millimeter.